Today, we're going to look at integration by substitution, or I'd say we're going to continue looking at integration by substitution, and we're going to think of this as the anti-chain rule. Recall that when we first started finding antiderivatives, that is, finding indefinite integrals, we took every fact that we had about derivatives and just turned it around into a fact that we now have about integrals or antiderivatives. One of the things that we'll have to turn around is the chain rule. So the chain rule is for finding derivatives. When we invert that process, we get a process called integration by substitution. So integration by substitution is the anti-chain rule. Let's remind ourselves of what the chain rule asks us to do. We want to find the derivative of a composition of functions, g of x plugged into f of x. The chain rule says take the derivative of the outside with respect to the inside, that is, find df dg, and multiply by the derivative of the inside, dg dx. So I take the derivative of f with respect to g and multiply by the derivative of g with respect to x. So that's the Leibniz style. Derivative of f with respect to g and multiply by the derivative of g with respect to x. Looks good in Leibniz notation because we can imagine the dg's canceling each other out, and we just end up with df dx. We want to look at the parts that show up in the chain rule. Notice that the outside function, the f, is what we take the derivative of with respect to g. So we take the derivative of f with respect to g, and then we multiply by g prime. There's the derivative of the inside that shows up from the chain rule. If g of x is just equal to x, then the derivative of x with respect to x is 1, and we get the same thing. So we're always doing the chain rule right from the start from a certain point of view. When we turn this process around, we're going to be looking for an outside function, an inside function, and the derivative of the inside. So if we integrate f prime of g of x times g prime of x dx, we'll just get f of g of x plus c. Plus c is our constant integration. Whatever constant we had with this f of g of x, we don't know what it was after we've taken the derivative, because the derivative of all constants is equal to 0. When we try to reverse the process, we don't know what the constant was, so we throw on that constant of integration. Identifying an inside and an outside, that's usually the easier part of the process. We want to make sure, if we're going to do integration by substitution, that we can see as a factor the derivative of the inside. So yesterday, the way I said this was the derivative of the inside as a factor is what makes integration by substitution work. This is how we know we can make this substitution. So we need the derivative of the inside as a factor. We need the derivative of the inside as a factor to make substitution work. We need the derivative of the inside as a factor to make substitution work. In the example that we had yesterday, we wanted to integrate the square roots of x cubed plus 1 dx. In this case, it looks like the x cubed plus 1 is our inside function, so that makes sense. It looks like our inside, our g of x, can be x cubed plus 1. And if we make g of x x cubed plus 1, then the outside, f prime of g, is the square root. So our outside function f prime of g is the square root of g. The reason that this is not substitution is we don't have g prime of x as a factor. So if I want to make this substitution where g of x is x cubed plus 1, g prime of x is 3x squared. We don't have a constant multiple of 3x squared as a factor in our integral, so this is not substitution. We don't have a multiple, a constant multiple of x squared as a factor. So this is not substitution. This doesn't mean we can't build an antiderivative, because we know from the fundamental theorem of calculus, we can always construct an antiderivative. We're just saying that substitution is not the way for this integral. So for example, if I wanted to integrate the square root of x cubed plus 1 times x squared dx, here we can do substitution. We'll say our inside is x cubed plus 1 I'm going to replace my clunky g of x notation with a, let's go with w. Our inside is going to be x cubed plus 1, just like before. Our outside function as a function of w is going to be the square root of w. To make this substitution work, to make x cubed plus 1 work as a substitution, I have to have a dw dx of 3x squared. I don't have precisely 3x squared, but I've got x squared, which is good enough. We do have a constant multiple of 3x squared as a factor. So substitution is how we can go about this integral. I've identified an inside function, x cubed plus 1. I said that is plugged into a square root function. That's the thing that we're actually going to be integrating. And we have the x squared, or at least a constant multiple of 3x squared, because we've got this factor of x squared right here. So that x squared is there to be the derivative of the inside. So in another context, we're comparing something like the integral of sine of x cubed plus 1 dx versus the integral of x squared times the sine of x cubed plus 1 dx. This first one is not a substitution. I want the inside to be x cubed plus 1. I need a factor of x squared that I don't have. The second one with this factor of x squared, This is substitution. It's that derivative of the inside that makes the substitution go. So let's learn the mechanics of the substitution process. Now that we know what we're looking for, we've got to think about the mechanics. We've got to think about what moves we're going to make. When we're thinking about doing substitution, once we have decided that we can do substitution, the thing that we have to remember is that all x must become w. We got to make sure all the x's become w. This is including the dx. That's going to be one of the x's that we need to replace, the one that has the dx attached to it. Let's see how it works. Let's suppose I wanted to integrate. I'm going to go with 3x squared for now for our first example. The identification phase is we decide what we want to be the inside function. So I'm going to say our inside function, it looks like this x cubed plus 1 is sitting inside this square root, so that's going to be w. W is x cubed plus 1. The outside function is the thing that we're actually going to integrate. So our integral is going to become some multiple of the square root of w. So if w is equal to x cubed plus 1, then dw dx is 3x squared. And we're going to notice that the 3x squared and the dx is equal to dw. dw is equal to 3x squared dx. So I can replace 3x squared and the dx with dw. So my integral becomes the 3x squared dx, all that gets replaced by dw. The square root of x cubed plus 1 gets written as the square root of w. Now I've traded my integral dx for an integral dw. There are no more x appearing in my integral, so I can proceed with my integration. This is w to the 1/2 power. So the antiderivative is w to the 3/2 times 2/3. And then we put plus c because we've done some integration. And now I can replace the w with x cubed plus 1. So now this is equal to 2/3 times x cubed plus 1 to the 3/2 plus c.
Hey, Professor, can you tell me how you got 2/3 w to the power of 3 over 3 2's?
Yes, we add 1 to the exponent and divide by the new exponent. So the integral of w to the 1/2 power is we add 1 to the exponent, so 1/2 plus 1. That's,
Oh, so you're finding the antiderivative of it.
Yeah.
Okay, makes sense. Got it.
so that's going to be w to the 3/2, and then we divide by the new exponents. So 1 over 3/2 is 2/3. So what we're looking for is at something that we can see is going to be an inside function. Then we identified the outside function, the thing that's going to be the function that we're actually integrating in the process. And then we look for the derivative of the inside. Do we have a constant multiple of the derivative of the inside to serve as dw? Because all these x's must become w's. The x cubed plus 1, that gets replaced by w. And the 3x squared and the dx, those two factors together, became the dw. So it's 3x squared dx. All those factors are in that dw. Once again, we want to identify something as being the inside function. Then we want the derivative of the inside and the outside function. In this case, we got 3x squared times sine of x cubed plus 1. It looks like that x cubed plus 1 is the inside of the sine. There's a composition where f of g of x, where g of x is the x cubed plus 1. And so w is x cubed plus 1. And our outside function, the one we're actually going to be integrating, is the sine of w. So if w is x cubed plus 1, I'm going to need to do something with this 3x squared and the dx. dw dx is 3x squared. Just take the derivative of w to find out what you need to make substitution work. If we want to make this substitution, then dw dx has to be 3x squared. And so I'm going to turn this around to solve for dw. And dw is 3x squared dx. And I think, do I have a 3x squared and a dx? Yes, we do. So rewriting this integral, our integral in x becomes the integral of sine of w dw. So we've traded our integral with all this complicated stuff around it, 3x squared and the x cubed plus 1, and shrunk it down to integral of sine of w dw. The integral of sine of something is negative cosine of that thing, plus some constant integration. And w is x cubed plus 1.
Professor, wouldn't it be positive cosine?
The derivative of cosine is
Or-
negative sine. So the integral of sine is negative cosine.
Oh, okay.
Now in this case, I set these problems up to be super obvious because I use the whole dw. dw dx is 3x squared, and we had a 3x squared. That part can be off by a constant multiple, but nothing else. So if, for example, I had something else like 5x squared times sine of x cubed plus 1 dx. The same process happens. We look for an inside function. It looks like there's a composition happening here where the inside was an x cubed plus 1. And my outside function is sine of w. So that part is the same as the previous one. To make this substitution work, to make x cubed plus 1 work as the substitution, then dw dx is 3x squared. And we notice that we don't have 3x squared, we've got 5x squared. What we can do is say, well, oops, this is not equals, because I'm going to be moving things around. The important part of the dw dx is the x squared. So I'll say that dw is 3x squared dx, so that 1/3 dw is x squared dx. I can be off by that factor of 3, because I can just move that over to the dw and say x squared dx is 1/3 dw. And the 5, I'll just carry along. So my integral in w, the 5, I'm just keeping. I'm integrating the sine of w, so sine of w. And in this case, the x squared and the dx, I left the 5 behind. X squared dx is going to be replaced with 1/3 dw. We didn't see this in the previous example, because the previous example had a 3. And if I put the 3 over here and I would have divided it by the 1/3, or I would have multiplied it by the 1/3, and they would have canceled. And that's why we just see 1 dw up here. 1 dw. But here, I'm just replacing the x squared and the dx with 1/3 and the dw. And so we integrate. The integral of sine is negative cosine. Don't forget your constant of integration, so because you don't want to lose a billion points.
Hey, Professor, I still don't quite understand how you got the 1/3 dw equals x squared dx.
Multiply both sides by the dx. So I have dw dx. dw over dx is 3x squared. If I multiply both sides by dx, then dw is 3x squared times dx. And then if I divide both sides by 3, 1/3 of dw is x squared dx.
Got it.
So here are the mechanics of what we were talking about yesterday. The goal is to not write down all the mechanical bits. You don't need to write down your new integral in w, and then integrate in w, and then plug back in the x. Your goal is to identify this as substitution, recognize what's making the substitution goes as x squared dx, and knowing that this 3 is going to show up as a 1/3, and then just writing the answer. All right. So the goal is to not write down all these steps. That's why it's counterproductive when your instructor's like, "Oh, show all relevant work. Show all of your steps." That's the worst one. At least when someone says, "Show all relevant work," they can say, I want you to write down this substitution, the DW. I want you to write, and they could mark all this as relevant and say, that's what I'm asking you to show. In which point you say, all right, I'll write that down. But when someone says, show your work, if you can go right from the integral to the, if you can go right to the answer without writing anything down, then your work is the empty set. You just write down the answer. And so if someone says, I said, show your work, you say, I did. You know what I mean? I got no problem with teachers that want you to write all this stuff down, but they do need to define their problem and say, this is what you need to show. Otherwise, it's a guessing game. And the speed limit isn't 65 anymore, is it? That's why I like math. Stuff is well defined. In fact, the phrase well defined is well defined. We actually mean what we say. We don't just try to come up with some kind of meaning based on the words that we're using to describe something. That's why the great shame of math education is that we have to teach it in some verbal language. Because every language that we use to communicate other ideas is not up to the task of communicating mathematics. What are we talking about? Oh, yeah. Keep in mind, it's going to be, there are the problems with spoken languages and written languages is that you might think your language is super consistent, but at some point there's a rule that you apply and someone that's learning the language will say, wait, do we do that all the time? And you're like, oh yeah, oh wait, no. Here are some cases where you don't do that. Here are some cases where that doesn't mean what it sounds like it means. I know you're thinking that couldn't happen in my language. But then I'm going to say, yeah, no. And even though I use two words in direct opposition to each other, you know what I meant. You want to go see this movie? Yeah, no. Two words, opposite meanings, answering a yes or no question, you still know what my answer was. You know what I mean? It's better language. Like in American, when someone's like, "Oh, hi, how are you?" They actually probably don't care how you're doing. That's just how we say hi. It's part of saying hello. If you really want to make it awkward, when you're walking by someone and you're clearly just acknowledging each other's presence and you're like passing each other in opposite directions in the hall, say, hi, how are you? And then stop and look at them like you expect an answer. And then they walk by all confused because they're on their way somewhere. Mutter under your breath as you walk away, rude. And then maybe we could stop this, hi, how are you? Now I fully recognize that I do this all the time. We're not trying to be perfect. We're trying to be better. So let's talk about an example of when we can't substitute and how the method is going to show us that we're not going to be able to substitute. So let's suppose that we have the integral of x times the square roots of 3x squared. Sorry, That's the example that does work. And this lecture is all about the x cubed plus 1 being the inside function. The process works the same. We identify something as being inside, and we say, I know what the inside is. It's the same inside we've been using every day. W is going to be x cubed plus 1. Then before we start moving on to the derivative of the inside and all that nonsense, we say, okay, if W is x cubed plus 1, if that's my inside function, what is it plugged into? At which point you say y is the square root of W. That's the thing that we're actually going to be integrating. We're integrating a square root function. Now we say to ourselves, what do we need to make this substitution work? What do I need to make this substitution? I need dw to be 3x squared dx. I need dw to be the 3x squared dx. The problem here is I've got the dx and only an x. I don't have a constant multiple of x squared dx. I've only got x. We only have an x, not an x squared. So this is not substitution. This substitution, w equals x cubed plus 1, we can't make because I need x squared dx to be the dw, and I've only got x dx to be the dw. Let's suppose that we have too much. Once again, the process starts off the same. We identify an inside and an outside function. Then we go to check to see if our substitution is going to work by looking for the derivative of the inside. So here, if I want my inside to be x cubed plus 1, first I want to make sure that I know what I'm plugging this into. And that's still just a square root of w. And then I'm going to need to look for the parts that make this substitution work. If w is x cubed plus 1, then dw is 3x squared dx. Now in this case, I have x squared dx, but I've also got this extra x that I don't know what to do with. I have enough x to make the substitution. Let's get rid of the 3. So I can read this problem as x cubed contains an x squared. And then there's a square root of x cubed plus 1. The dx can be part of the x squared. But over here we had an x cubed, so I've got this extra factor of x that won't be substituted by anything that we have so far. We've got this extra factor of x. And the first rule of substitution is that all x must become w. This x squared and the dx can be replaced with a 1/3 dw. And we can still have the square roots of w. But all x must become w. All the x's must be substituted. No x left behind. So this is not substitution. I just spelled work W-R-R-K, which strangely still works. This doesn't mean that we're completely without recourse on these problems. It's just that this substitution is not going to work.
Professor Lisha, I have a question, please. If there is no substitution, then we just leave. So we need to take antiderivative. What is it?
We'll need to do something else.
Okay.
That's all. At this point, that's all we need. That's all we know. We need to do something else, and we don't know. And at this point in our mathematical careers, we don't have another thing to do. We know one trick, and so if the problem doesn't exploit that one trick, then we just have to wait for other methods to show up.
One more thing, Professor Lich. Why the in further down the road? What is the substitution? What does it mean?
We're just substituting one variable for another. We're substituting our x integral, our integral in terms of dx, for an integral in dw.
Yes,
That's
yes.
the substitution. We're substituting w for x.
And this function is trying to tell something. The function is it?
What function? Try to tell. What's the function that you're referring to?
Oh, I mean, like why we need if the function with two different variables, then we put the substitution to one the same.
We won't be working with functions of two variables. We only get to use this is single variable calculus. We only get to use one variable.
Maybe it was something else. Thanks, Professor Lish. Thank you.
Okay. It must have been something else you were looking at, because we're not allowed to use more than one variable. We spend 2 semesters of calculus under very harsh restriction. We only get to use one variable. Then we get to Calc 3, multivariable calculus, and we get to use more than one variable. It's like, oh man, this makes things so much easier. But the reason we don't start there is the same reason in physics. We start by ignoring air resistance and ignoring friction. It's the same reason we don't take babies as soon as they start to become toddlers and put them on motorcycles. You know what I mean? All right. Especially in the United States, because as soon as you're get your motorcycle license in the United States, you can buy a big overpowering motorcycle that you're in no way qualified to ride. Anyway, what are we talking about? Oh yes, substitution. So it doesn't mean when I say that this substitution won't work, it's not that substitution in general won't work. We just or that there's no antiderivative, because we could always construct one if we need to. It's just that this particular substitution that we've chosen won't work, either because I don't have enough X to make the DW, or I have an extra X that's not covered by what I'm replacing. How's everybody okay? Tomorrow, we're going to look at some what I refer to as stupid substitution tricks. But that's a reference to a Dave Letterman sketch, and he's not even on television anymore, so no one gets it. So I should just shorten that to substitution tricks. So we're going to look for some ways that we can get around this substitution bit. The driving factor is going to be all X must be substituted. All the X's have to become W's. We have to know when a substitution isn't going to work so that we know when we can manipulate substitution to make it work for us. All right, that's for tomorrow. That's going to do it for today. I'll see you all on tomorrow. Everybody have a good day, and thanks for playing.